Hello everyone, this is Moteb Alghamdi from the University of Manchester EBIT Group. I am joining OCL 2020 with a poster that is titled Concurrency Mapping Study of an HPC Application Kernel to Zynq UltraScale-Plus FPGA with Xilinx SDSoC OpenCL. In this video, I'm going to share with you the poster content as slides. Those slides summarize a small part of my PhD work, which involved the study of exploiting multiple kernel, multiple FPGAs in the context of weather and climate application for EuroEXA project. In this poster, I am discussing the mapping options of parallelism types that an HPC application can have to the FPGA. What we are going to look at in this slide, and those slides, are the mapping options technique and study and exploration study of which of one of them is gonna provide better solution for the kernel. This study is carried in the point of view of a software programmer who have a little hardware design knowledge. The kernel we are targeting is a kernel from shallow water HPC application. This kernel is to define a difference, which modeling the behavior of climate change. The time stepping loop runs for 4,000 iterations, means this kernel will be called 4,000 times. This kernel has 3 inputs and it's produced 3 output CU, CV, and Z and H. There are no data dependency between those calculations. So an example kernel could have 3 types of parallelism in such behavior, like instruction level parallelism, data parallelism, functional parallelism. So which one of those parallelism, if it's been enhanced and mapped to the FPGA, going to provide a better performance or better solution for the kernel? In addition, this kernel could be written in 3 forms, as coded as one loop for all the calculation. It can be written as a loop pair calculation like this one, or as a function that's being called. So the code options and the parallelism options we can enhance could affect the FPGA design. So what are the options from the FPGA and the programming level could be used to map those concurrency and to explore those options on the FPGA? There are different mapping options from 2 levels. The first level is the OpenCL language mechanisms or level, where and the other one is the SDSoC FPGA level. So in the OpenCL language level, we could choose between the use of a task kernel as one work item, or NDRange kernels with multiple work items. The type and the number of command queue choice, and the number of kernel. We can write this kernel in as a single or multiple kernels. And from the FPGA side, we have the pragma or attribute dataflow over functions or over loops, which could map the functional parallelism to the FPGA. And the choice of number of compute units mapping option. So those mapping options or mapping mechanisms can be optimized. And there are options of optimization from both levels, the FPGA level and the OpenCL level, which make it interesting to explore the choices in terms of mapping mechanisms and the optimization mechanisms to reach the best implementation. So from the OpenCL, for example, there is the data transfer options and method between the host and the kernel, and also there is the utilization of the full width or bandwidth of the data access ports between the host and the FPGA and the kernel in the FPGA using factorization, and the utilization of the memory hierarchy in the FPGA system we are targeting. In the FPGA side, we have loop unrolling and loop pipelining pragmas, which can be used to map the instruction level parallelism and improve the calculation throughput. Also, the utilization of all the available global memory ports, which is called max memory ports, and providing more memory access in the FPGA local memory by partitioning that local memory or the arrays, local arrays, for more parallelism. And we have another optimization method, which is inferring the first transfer from and to the global memory. So in the last two slides, we have seen that there are many methods and options for mapping kernel concurrency to the FPGA. So those options leading to question about the performance from the choice we are going to make and the impact of that choice on the resources usage, and what outcome FPGA hardware design we will get out of our choice from that mapping options and optimizations. And of course, the programmability in the point of view design programmer in terms of development time. So to set up the experiment, we have chosen 64 by 64 problem size as a case study for this poster. Firstly, we have run the kernel without any optimization or mapping methods. And this kernel took over 3 minutes to be executed and to finish the 40,000 iteration calls. And then for the preparation for the mapping experiments, a big space of optimizations method has been explored to apply on the kernel to be applied on the mapping options method that we are going to carry on the kernel. So this figure shows the optimization method effect that we are going to use with the mapping method. And from the left, we started with the use of max memory port, and building on top of that, the other optimizations options we have, and we see to see the effect of the use of them, and to choose the optimization method that we're going to apply on our experiments. This slide shows only the best performance result of our mapping, concurrency mapping exploration study. When The kernel was coded using code option number 1 to try enhancing the instruction level within that kernel using the task kernel mapping method. The kernel finished the execution in 1.16 seconds. And the best implementation we have found with mapping the functional parallelism of our kernel, where we can map that functional parallelism with the use of multiple kernels, where each kernel compute a different calculation of that kernel. For example, a kernel for CU, a kernel for CF, and a kernel for Z, and a kernel for H. And we execute all of those kernels in parallel. Or the use of dataflow for functions and loops over that kernel. So we coded the kernel for the functional parallelism with code option 2 as functions, or code option 3 as loops. So with dataflow loop, as a function parallelism, it provided the best mapping performance with 0.888 seconds, while the use of multiple kernels to enhance the functional parallelism provided less performance. In terms of data parallelism, enhancing the data parallelism with that's been applied with the code option either number 1 or 3. After many parameters tuning and experiment of choosing the size of the NDRange group size, the best implementation was the use of one compute unit with one work group of 64 by 64 work items, and that deliver performance or execution time of 1.92 seconds. Therefore, in terms of performance, we can see in conclusion that the use of code option, mapping option data flow over loops provided the best concurrency mapping performance for our target kernel. If we look at the resource usage figures, we have in the left the resource count of the FPGA we're targeting. The bar graph shows that the NDRange kernel mapping options resources usage was the efficient one. It utilized a tiny bit of resources in that FPGA, which means that this design option can help to replicate the kernel many times as much as the FPGA can fit to enhance the spatial parallelism. Nevertheless, data flow loops mapping option which provided the best performance, it also utilized less than 10% of the FPGA resources, which also give good opportunity to boost the performance through the replicating of the kernel design to enhance the spatial parallelism. However, multi-kernel mapping option for functional parallelism and task kernel utilized a considerable amount of resources. This final slide shows a summary of the outcome hardware and the programmability of the different mapping options we have targeted in our experiments. So the functional parallelism with multi-kernels required functional parallelism with multiple kernels and data flow loops required a number of compute units. For example, data flow loops required 11 compute units as a hardware outcome. In terms of the host programmability, we had to use out-of-order command queue to run the 4 compute units of the multi-kernel mapping option in parallel. And in the kernel side coding, 11 loops and 14 loops in multi-kernels and data flow loops that targeting functional parallelism was required, while no loops was used in the NDRange kernel. In terms of programmability, the easiest mapping option to program was or to code was the task kernel, while NDRange option, mapping option, was a difficult one to get it working right. And we have, as we have seen in the last, in the previous slide, that multi-kernel utilized the highest amount of resources of our target FPGA, while NDRange provided or consumed low resource usage. Thank you so much.